Okay. Hello everyone. Welcome back to our channel. Today we'll discuss one more question, and before going to that question, I would like to discuss something about the distribution of identical particles or distribution of particles in different states. Okay. So actually, I will add this to continuing of the previous video. So, if we'll say, as we know, that the particles, if we'll consider the identical particles, we can distribute these identical particles. Then I will jump to the question. So these identical particles, they are like two kinds. We know that one is distinguishable, which we can distinguish easily, and another is indistinguishable. Okay. Okay. This distinguishable particle means the distance between this particle is very greater than the wavelength. So that's why we are calling we saying this is distinguishable. We can distinguish them, and in indistinguishable case, the distance is that is r. R is very less than the wavelength. That's why this is indistinguishable. When we says indistinguishable, that indicates that the r is very less than lambda, and for distinguishable, r is very greater than lambda. So this is like classical, this obeys the classical laws, and that is Maxwell Boltzmann statistics, that is MB statistic, or we can say MB statistics, that is Maxwell Boltzmann statistics. Okay. Okay. And when we consider indistinguishable, again this is the quantum mechanical concept. This obeys the quantum rules and quantum mechanical theories and all, and this is like distinguish. Again it is differentiated as one is the fermions. We know that these are fermions and bosons. So basically these according to the according to their spin and their distribution, we have we like it is they are separated. That's why one is fermion and others are bosons. Okay, and these fermions, they obey Fermi-Dirac statistics, and this obeys Bose-Einstein statistics. Okay, this obeys Fermi-Dirac statistics, this obeys Bose-Einstein statistics, and the spin of the fermion is the half integral. These are half integral spin, and bosons have integral spin. Okay, these are half integral spin, these are integral spin, and for this case the wave function is antisymmetric. For fermions the wave function is antisymmetric, and for bosons the wave function is symmetric. Okay, and this obeys Pauli exclusion principle. So we have to consider the Pauli exclusion principle when we distribute this particle in different states. But for this case, there is no restriction. There is no restriction. Okay. I hope everyone is okay with it. Now we'll just see how we'll distribute. Actually, today will basically from the statistical mechanics, you will see from this part you will get questions like related to the partition function. Like you have to find out the partition function for different like for MB statistic or FD or PE. Like the question is given like that, there are such like particles and they are distributed in different energy states. So find out the partition function for this particular this particular distribution. Okay, and next we will get questions like for distribution function, distribution part, that is distribution means that is we'll get question how many ways, number of ways of distribution. Okay, so that is omega or w, we can say w, sorry, this is w. Okay, and you will see, and we'll discuss this distribution part today, and in the next video I will discuss the partition function part. Okay, so number of when we say number of ways means if there are like there are n particles, and in how many ways we can distribute this particle in different states. Okay, for Maxwell-Boltzmann state, like if I have states like this is state 1, state 2, these are the energy states, state 3 and so on, and these are having energies E1, E2, E3 and so on, then how the particles will be distributed in these things. So that depends on these things, whether they are there is having some restriction or not, whether we can they will obey Pauli exclusion principle or not, depends on the fermions, bosons and all. Okay, so when we say like okay, so for the case of Maxwell-Boltzmann statistic, we will say the first case, that is MB statistic. I am writing in short, so that is MB statistics. So for MB statistics, okay, we know that for MB statistics there is no restriction and they are distinguishable. We can distinguish them. So if we will distinguish them, then we it is easy for us to distribute this particle. Yes or no? If we distinguish them, if there is no we cannot distinguish them, then there will be more number of ways to distribute these particles. Okay, so for the case of Maxwell, like if I'll say there are two particles, let there are two particles, and as they are distinguishable, I can name them like A and B. They are two particles, and they are distributed in two states. So I can like A, B can be in these states. Another is like we can distribute A, B can be in these states, and A can be here, B can be here, and B can be here, A can be here, because we can distinguish them, right? So that's why this is the case of the Maxwell-Boltzmann statistics. Okay, so for number of ways to like number of ways of arranging N1 particles in these states, we can write okay, we will find that. Now we will see how a number of ways to distribute the particles. Okay, so for number of ways, number of ways. Okay, so if I am considering that if there are N1 particles, so to distribute, and there are states like there are N states. So without degeneracy, we are considering without degeneracy. Okay, so what is degeneracy? If more than one states are like having same energy states, that then we are saying that that is the case of degeneracy. Okay, so number of ways of arranging, if I will consider, let I have n number of n states and having n1 particles. So to distribute to arrange n1 particles, we will have like omega 1, like just I am giving a hint, that will be n factorial divided by n1 factorial n minus n1 factorial. So if I will just by taking then the next particle, when I will arrange the next particle, the number of states will be n minus n1. So this will become n minus n1, yes or no? Now there are n states available. There are n states available for n1 particles. Now if I will arrange n1 number of particles I arranged in n states, according to this, then the number of available state becomes n minus n1. Accordingly we will distribute these states, and at the end we will see, I am not going into the total derivation. See, the w2 will become, just I am doing this one, w2 will becomes n minus n1 c n2. Okay, so here I will get like something n minus n1 factorial divided by n2 factorial, n minus n1 minus n2 factorial, so on. So this will go on, and at the end the total number of ways will be as total number of ways, as this is multiplicative, we have to like w1 into w2 and w3 and so on, and we will get w is equal to n factorial by n1 factorial, n2 factorial and so on. This is the case of no degeneracy, when there is no degeneracy. Okay, and when we will consider the degeneracy case, for the degenerate states, for degeneracy, just I am writing down, we have to remember these things. WMB I am denoting like this. This is no degeneracy, and for degeneracy case, this Maxwell-Boltzmann's distribution of ways is becomes like this is degeneracy. This becomes okay, because now for degeneracy case we will get GI. These are the number of states. Okay, so this becomes n factorial pi I, that is product rule, GI by to the power ni divided by ni factorial. Okay, this is the case of Maxwell-Boltzmann statistics. Okay, now we will move to the second one, that is the case of Bose-Einstein distribution, and that is applicable for bosons. As we have seen, that is applicable for bosons, and for that case there will be no restriction. For that case there will be no restriction, and the particles are distinguishable. So when we are considering Bose-Einstein statistics or distribution, Bose-Einstein distribution, okay, this is Bose-Einstein distribution. So for this case we know there is no restriction for this case, and particles are indistinguishable. Okay, we can distinguish the particles. So that means what? If there are like particles, we can distinguish them. If there are 3 particles we are saying, so that means, let's take the easier one, 2 particles. So that means the particles are like AA. We can distinguish which is one, which is what, which is which one. We can distinguish them. So if there are 2 states, then we have to distribute like if they can be here, they can be, let's take this one here, and one more state they can be here. We can take the both case as in the Maxwell-Boltzmann distribution. We can distinguish, there will be one more step, one more distribution will be there, but this case there will be no extra cases. The particles will be distributed like this. Okay, so okay, we will see for 3 states also. I will discuss it in later. Okay, so for this case, if the degeneracy is GI and there are Ni particles, so for that case, if the degeneracy is GI, or that is the number of states, degenerate states, okay, GI, and the particles are Ni, then because here we will take it account the degeneracy case. Okay, so number of ways, you have to remember this one, number of ways to distribute the particles in these Ni states, sorry, GI states, this is number of particles is equal to, this is Ni plus Gi minus 1 Cni. So to distribute Ni particles in this states. Okay, so there will be total number of ways will be equal to Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. Okay, this is the case you have to remember. Okay, now we'll jump into the Fermi-Dirac statistic. Okay, and the last one is the Fermi-Dirac distribution. And for Fermi-Dirac distribution, we know that these are fermions, and they are having half integral spin, and they obey the this one is the important thing, they obey the Pauli exclusion principle. So this Pauli exclusion principle, what is this Pauli exclusion principle? That it says no more than 2 electrons can occupy a same orbital state or a same energy level. So more than 2 electrons cannot occupy a single orbital state or a single energy level, and the only the opposite spin can occupy a same energy level, and same spins cannot occupy the same energy level. That is the Pauli exclusion principle, right? So this for this case, these fermions, like if as we just discussed, if we will consider two particles and they are having opposite spin, like this is having spin up, and this is same spin. Okay, same spin. So if they are same spin and we are distributing in two states, so what will happen here? They cannot be in the same states. Okay, if I will consider opposite spin, so then they can occupy the same state, and here they can be, and as they are indistinguishable, we cannot say which one is at which level, something like that. Okay, so now we'll discuss this one, okay, later. The number of ways we can distribute the particles or the fermions in the energy levels is given by Gi is the number of states, degenerate states, by Ni factorial. You have to remember these three three formulas related to the distribution, like from Maxwell distribution, and for Bose Einstein distribution, and Fermi-Dirac distribution. Okay, so this is the distribution this is the number of ways we can distribute the bosons in the energy states which are indistinguishable, and also for Fermi-Dirac the particles are indistinguishable and they obey the Pauli exclusion principle, and for this case we can that means more than 2 electrons can occupy a same energy level, and this is the Gi is the degenerate states, Ni is the number of particle, and this is the Fermi-Dirac distribution. According to the Fermi-Dirac distribution, this is the ways, number of ways we can distribute the particle according to the Fermi-Dirac distribution, number of ways we can distribute the particles according to the Bose-Einstein distribution, and we have here number of ways we can distribute the particle in Maxwell-Boltzmann distribution, which is classical part. Okay, so now we will just discuss little bit. Okay, see, let we have before going, there is a question, actually I will solve that question, net question. So let just differentiate these things. If we have two particles and we have three states. Okay, if we have two particles and three states. Let's see the difference. Okay, we have two particles and three states. Okay, three energy states. Okay, if this is the case, for Maxwell-Boltzmann, we'll see how to distribute, and for Bose-Einstein, we'll see, and for Fermi-Dirac, we see. Okay, so for Maxwell-Boltzmann, as these particles are distinguishable, okay, and for these two cases, we have particles are indistinguishable. Okay. Okay, so I am just giving the hint, I'm not writing it. Okay, so for distinguishable, that means we can take the particles as A, B. As they are indistinguishable, we can take particle A because they are indistinguishable, so we can distinguish those particles. Okay, so for this case, let's see the distribution. Okay, so if there are three states, what are the number of ways? Okay, so let this the first way. I'm just, okay, if there are three states, I'm just dividing it here. Okay, I will do that later on. If I have three states, I can distribute these particles. First here, the particle can be A can be here, B can be here, and then I can distribute like A can be okay, so A can be here, B can be here, and next I can distribute A can be here, B can be here, and we can distribute like A can be here, B can be here. So similarly, like I think I will get okay. Now if I'll distribute, I can keep A here, B here, and B here, A here, and there will be more three states like A, B can be here, A, B can be here, A, B can be here. Okay, so like there are like just a second, A, B can be here. These are the number of ways: 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 ways we can distribute the particles here, and the formula is like this is G1 power n. Okay, so if there are number of that is the number of ways we can distribute. So there are number of states like 3 states, and number of particles there are 2, so the total number of 9 ways. Okay, Gi is the number of states, n is the number of particles. So according to Maxwell-Boltzmann, see, just we can distribute, because as they are distinguishable, we can keep them anywhere. Okay, but when we are considering the Bose-Einstein state, okay, I'm just doing this. Okay, so for this case, these particles are indistinguishable, right? And there is no restriction. So that's why, like if there are 3 states like this, 1, 2, and 3 states. So first the particle can be A can be here, A can be here. Okay, this is the first state, first distribution. Next we can distribute like A can be here, A can be here. Next we can distribute A can be here, A can be here, and next we can distribute A both can be in one state, both can be in the second state, both can be in the third state. So the number of ways are 1, 2, 3, 4, 5, 6. There are 6 ways. Okay, and if I will put the formula, if there are two particles and 3 states, I can find out like the W according to the Bose-Einstein is equal to Ni plus Gi minus 1 factorial. I just given you this formula, that is Ni factorial Gi minus 1 factorial. Okay, so 2 particles, so 2 plus 3 minus 1 factorial divided by 2 factorial, 3 minus 1 factorial. So this gives me like this is 4 factorial divided by 2 factorial into 2 factorial. This will give me 6. Okay, now come to this one. As here there is restriction, there is restriction, the particles when we distribute, that is no two particles can occupy the same spin. So if there are three states, right? Okay, so if they are indistinguishable, A can be here, A can be here, A can be here, A can be here, and A can be here, A can be here. Okay, so number of ways is equal to, according to the formula we got here, 3, and according to the formulaic statistic, that is gi factorial divided by ni factorial, gi minus 1 factorial. Gi is the number of states. There are 3 states. How many particles are there? 2 particles. So 3 factorial divided by 2 factorial into 3 minus, sorry, this is gi minus ni factorial. Okay, so gi minus ni, so this is 3 minus 2, so we got here 1 factorial, and the answer is 3. Okay, I hope you guys are clear regarding this. Okay, now we will jump into the question. Okay, if there are 3 parts, we just saw if we have 2 particles and 3 states, how the particles will be distributed according to the Maxwell-Boltzmann, Bose-Einstein, and formulaic statistic. Okay, and this is for bosons, this is for fermions, and this is for classical particles. Okay, so we'll come to the question. So this is the question which was in June 2018. Okay, so the question says the number of ways of distributing 11 indistinguishable bosons in 3 different energy levels is. So as just we have discussed that, see, there are 11 indistinguishable particle. So indistinguishable particle means either these are bosons or fermions. Now it is, we know this is bosons, and for bosons there is no restrictions. So we will just jump into the formula. W is equal to Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. Okay, so Ni plus Gi means we have number of particles here. Ni is the number of particles, that is 11. Gi is the number of states, that is 3. That is, there are 3 energy levels. So 11 plus 3 minus 1, so that is 13 factorial divided by we have Ni factorial, that is there are 11 energy levels. Gi minus 1, that is Gi means 3 states are there. Gi minus 1, that is 2 factorial. This is my answer. Easy. So this is the question. So you have to just remember, when you will get these questions now, you will from this section you will get questions like to find out the number of ways, to find out the partition function and all. So the energy, to find out the mean energy, as we have discussed it earlier. So we'll see in the next video how to find out the partition function. Okay, I will do in one more video. Okay, thank you everyone. Stay safe and take care. If you have any questions regarding to these sections, you can comment below, and so that we'll discuss, so that we can discuss it later on. Okay, thank you guys.